Hi, in this video, we're going to look at some simple examples of momentum conservation. So let's get started. Graham and Nina are on their first date at a mini golf course. Nina puts her ball B, toward the hole, and in a desperate attempt to impress his date, Graham puts his ball a second later so that it bumps into Nina's ball, which was still moving. The momentum vectors of the balls is shown before the collision and after the collision. Which vector below would represent Nina's ball after the collision? Assume the two balls make up an isolated system. So I hope you can visualize the situation. This is one of the balls here. This is the second ball that was putted. This is the first one. So the second ball is behind the first one and it catches up to it and it bumps into it and it passes on some of its momentum. So we're given vectors here to show how much momentum we're dealing with. We don't have numbers, we just have a visual representation of how much momentum there is. A bigger arrow means a larger amount. And in this case, we have little tick marks to indicate just how much there is. So this would be 1 unit of momentum here, and this would be 2 units of momentum. So it appears that whatever units we're dealing with, the momentum of ball A is 2 before the collision, and the momentum of ball B is 1 before the collision. Now, after the collision, ball A has a momentum of 1, and we don't know what the momentum of ball B is after the collision. But if you remember you remember the law of momentum conservation, as long as these two balls are in an isolated system, then their momentum can pass back and forth between each other, but the momentum is never lost, it never goes away. So the total momentum before the collision, I'm going to write total PI, total initial momentum here, is 2 plus 1. So 3 units of momentum. That means that the total final momentum should not change. And so it should still be 3. So now it's just a mystery of, okay, what's this missing quantity right here? Well, it's got to add up to give you 3. We have 1. So 1 plus what is 3? This momentum should be 2 as well. And it's still in the positive direction here. 2 plus 1 gives you a total final momentum of 3. So we need to choose a vector that has 2 units of momentum to the right. And so that would be this choice right here, choice B. Let's look at another example. All right, let's just get it more simple here. It says two objects, A and B, collide in an isolated system. The vectors below represent the before and after collision momenta of objects A and B. Find the missing momentum vector. So this time we don't know this initial momentum of object B, but we have the initial momentum of object A, and we have both of their after collision momenta. So to find this one, we're going to have to do some, let's just write down how much momentum we have here. We have a positive 3 for the starting momentum of object A. But then after the collision, the object A is now moving in the negative direction to the left. So this is a negative 1. We only have 1 unit here. And then this momentum for object B after the collision is a positive 2. So we're missing this quantity right here. But we do know if we add these two together, the final momentum total is negative 1 plus 2. So that's a positive 1 unit. So the total momentum after the collision is positive 1. The total momentum before the collision should be the same because we don't lose any momentum in an isolated system. It stays the same throughout. Okay, so that must mean if this is positive 3 and we should have a total of positive 1, this is negative 2. So a momentum to the left, 2 units. So that's going to be, these are the ones to the left, that's going to be F. All right, let's do one last example. This time we have 2 carts of different masses, and they collide in an isolated system. The before and after collision velocities of the carts are represented by the velocity vectors. Let me move this up a little bit so I have some more space to, more space to work with. So now we're dealing with different masses for our starting objects. And if you just recall, momentum is mass times velocity. Okay. So here we have an object that's got a mass of 3m. We don't have numbers again for the number of kilograms. So we're just dealing with, 3m and m. So this is 3 and 1 for your masses. And the velocity here, we also don't have numbers. We just have a factor or a scale. So this velocity has 3 units, and this velocity has 1. So we have a mass of 3 and a velocity of 3 units. So we multiply these two together, 3 times 3, and so that's 9 units for momentum. So the P of object A, the momentum of object A at the beginning is positive 9. And then here we have a mass of 1 and a velocity of 1. And so the momentum of object B at the beginning is positive 1. So positive 9 and positive 1. So our total starting momentum is 9 plus 1. So that's going to be a positive 10. And that should also be the same over here because we don't lose any momentum. Momentum is conserved. So the total final momentum should also be positive 10. So now we can kind of work backwards and figure out what is our missing velocity here. First, let's figure out what's the momentum of the big cart. So we have a mass of 3, but now if you notice the velocity is only 2 units, right? So 3 times 2, that's going to be a final momentum for A of 6. 3 times 2 is 6, so that's a positive 6. We don't know the velocity over here, but we do know that the total momentum should be positive 10. This is a positive 6. I didn't write that very clearly. So we have positive 6 over here already. So this should be a positive 4, so that when we add up 6 and 4, we should get 10. So the momentum over here should be 4. The mass is 1, but we don't know that velocity. We know the mass is 1 because it's just the m. But to get a momentum of 4, that means we would need to have a velocity of 4. And so the velocity of this car must be 4 if you work all the way backwards there. It is in the positive direction still, so it's moving 4 units to the right. So we're going to choose option D for our answer here. 4 units of velocity to the right. So that's all I've got for you in this video. Remember, how you do anything is how you do everything.